So till now we are familiar with data structures like arrays, linked list, then stack, queue. So all these data structures are in some sense linear. These are all linear data structures. And typical operations take order n time. Means, for example, if you search an element in an array or linked list, then and if you try to insert an element in a linked list and so on and delete an element from a linked list, so typical operations take order in time, which is prohibitive, which we cannot afford, because n can be very large. So what is the goal? So why we want to look for another data structure is that often there exist hierarchies, there exist hierarchies in the data. So there can exist an hierarchy in the data. For example, if you look at, say, family tree. So who is parent of whom and so on, who is uncle, grandparent, grandchildren and so on. So there the data is inherently hierarchical. And not only this, for example, if you look at file structure in operating system in an OS. So there could be a root directory, and under which in a directory there can be some other directories and some more files, and within each directory there could be other directories and so on. So there exists an inherent hierarchy in the data itself. Okay, and also we would like to perform operations in order log n time. Instead of spending order n, we would like our operations like search, insert, delete to be in order log n time, which is exponentially faster. So these things are handled, or these things can be achieved using what is called a tree data structure. Tree data structure. So what is a tree? There can exist there exist several equivalent definitions of tree. So for this lecture, what we study is what is called rooted tree. So in this lecture I won't repeat every time this term rooted, but whenever I mention, I refer to a tree, then it means a rooted tree. So if not mentioned otherwise, there exists a root. Okay. Now what is the definition of tree? Tree consists of a special node called, say, root node, and it has 0 or more subtrees. So the definition itself is a recursive definition, which first says that empty set is a tree, and there exists a special node R, distinguished node R, and it has 0 or more subtrees T1 to Tk. Okay, and that's how it is defined. So, so the base cases for this recursive definition, single node is a tree, node is a tree and it is its node, and that node is its root. Okay. Uh, for concreteness, so let us also assume that that empty set is also a tree. This particular assumption will make lot of our writing easy. So empty set is also a tree, also an empty tree. Let's call it empty tree. Okay. So what is the example of a tree? So this is one node. There could be some data. For ease of exposition, we will assume that these data are simple integers, but these data can be any arbitrary information. So maybe 7. It has left child, say 3, right child, maybe 5, and some more left child and right child, and so on and so forth. Okay, so this is the root node. This root node has two children, namely this node with label 3 and this node with label 5, and this root node is the parent node of these two nodes, and these two nodes 3 and 5 are called siblings, and analogously you can define notions like grandchildren, grandparent, and so on and so forth. Okay. Now how we implement tree. So implementation. So what is the definition of a tree? So let's recall, it has a root and it has some arbitrary number of children, and arbitrary number of subtrees, and each subtree is a tree in itself. So one possible implementation in C is you define struct, then maybe node, which is a tree node, then maybe you have some data int, and then so suppose this is a particular node, and how many child pointers should be there. Now because the number of children could be arbitrary, so it does not matter how many pointers you keep. You predefine it 10 pointers or 20 children pointers. It may be insufficient in some cases if the number of children is more. So what is this? The way it is implemented is what is called left child right sibling implementation. So what is it? It's called, you write struct node star, this is left child, and then there is a next pointer. So if it has multiple children, then this particular node will have this some data, and it has one pointer which simply points to this left child, and there is another pointer which simply points to the next sibling. So struct node star left sibling, left sibling. So this particular node will have some data, and then one pointer which is points to the left children, and if it has some other sibling, then there is another pointer which will point to this next sibling. And now how I can, for example, I want to traverse through all the children of this particular node. Let's call this node V. And then what I would do is that I have pointer to its left child, and no, not left sibling, it is right sibling, immediate right sibling. Okay. Now what I do is that I have a pointer to the left child of the V, and I go there, and there I will look at the pointer to the right sibling, and then that's how I access the second child. And for the second child also there is a pointer which points to the right sibling, and that's how I can get access to the third children, and so on and so forth. Okay, so if our tree is a arbitrary rooted tree, then we use what is called left child right sibling implementation. Okay. Now let us see a special case which is called binary tree. What is binary tree? A rooted tree where every node has at most 2 children. Okay. So if this is a node, it can have one children which can be left children. This is one possibility. Another one is that it has a right children, and another possibility is that it has both left and right children, and another one is that it does not have any children. So these are the 4 cases, and here we can, because the number of children is bounded, it can be either 0, 1 or 2. We can implement it simply using struct node, then what you do is that first you have some field for data, and then a pointer to the left children, and then a pointer to the right children. Okay. So that's how a binary tree is implemented. Okay. Now once a tree is given, I want to sort of navigate through the trees. For example, let's take an example. So maybe let's take the above example that we have done. So let's take this example. Okay, and so wish to navigate or wish to traverse all the nodes, and there are 3 kinds of traversals. So tree traversals. For example, I want to search for a key in a binary tree, and then the simplest algorithm will be to traverse all the nodes in the tree, and look whether the key that you are looking for is present or not. For example, in this particular example of the tree, maybe I'm asked to find if say the key 8 is present or not. So I need to traverse all the nodes and look for the element 8 if it is present or not. So in various other kind of application, we may need to traverse the all the nodes of the trees. So there are tree traversals that is very useful. One is pre-order, another is in order, another is post order. Now what are they? Let's write it. So pre-order first traverses the current node, then it goes to left subtree, and then once left is finished, then it goes to right recursively. In order first traverses left, then it traverses the current node, then it goes to right. And post order first goes to left, then goes to right, then visits the current node. So let's see how the pre-order traversal will look like for this tree. So we'll start with the root node, and the pre-order traversal first traverses or looks at the data of the current node, which is 7. Then it goes on to the left tree, and recursively it will make a pre-order traversal for this left subtree. And how it will do? Again, it is at the current node 3, so it will visit the current node first, which is 3, and then it goes to the left subtree, which is singleton node 1. So it traverses 1, and that finishes the traversal of left subtree. Then the control returns to 3, and then it goes to 10, the right subtree, and that finishes the traversal of the left subtree of 7. Then it goes to the right subtree, which is 5. Let's see how in order traversal will traverse the nodes. So it will start at root, but it don't look at the data of root node first. It will first go to the left part, left subtree, which is 3, 1 and 10, and again it will recursively do the same thing. You don't look at 3 first, it will first go to the left subtree, and at 1 also it will do the same. It will first go to the left subtree, but it does not have a left subtree. This particular node 1 does not have a left subtree, so the control returns. Once it finishes left subtree, then it visits the current one, which is 1, and then it goes to right, but 1 does not have any right children, so that part is finished. Then the control returns to 3, and now we are done with traversing the left subtree of 3. Then we will visit the current node, which is 3, and then it will go to the right subtree, which is 10. Then once 10 is visited, then the left subtree of 7 is all the nodes are traversed, and now we will look at 7, and then finally 5. I would encourage you to try to write the post order traversal for this particular tree. Okay. Okay. Now there is something what is called say some more terminology for tree. What is the or depth of a tree, or let's define the path. A path from a tree node U to V is a sequence of vertices, sequence of nodes U0, U1 to UK, where UK is V and U0 is U, such that U0 UI is a parent of UI plus 1. UI is a parent of UI plus 1. So, U is somewhere here and there is a path to V. So, as you see that the convention that is typically followed, and we will also follow, that the edges are oriented from parent to children. So, if there is a path from U to V, that means there exists a children of U, there you go, and from here you go to its children, some appropriate children, and you finally reach V. Okay, and so that is the path. And what is the length of a path? Length of a path is the number of edges in it. Okay. Now, this path allows us to define some more concepts. So, U is called a predecessor of V. So, U is called a predecessor of V if there exists a path from U to V. And in this case, V is called the successor of U. Then V is called a successor of U. Then there is something called what is called depth of a node. Depth of a node, V is the length of the path of the root to V path. Okay, so that is the depth of node, and the depth of a tree is the maximum depth of any node. Okay, these are very common concepts. Now, here you observe that while we define traversals, now if we are if we don't arrange the keys in some particular order, then if I am given a particular key to search whether that particular key is present in this tree or not, then I have to traverse the entire tree. I have to traverse all the tree nodes. Now, that will be inefficient because the number of tree nodes is like the size of the data, and if I have to look at all the data points, then again I'll run into order n time algorithm. So, to take care of this problem, what is defined is what is called binary search tree. Binary search tree, BST in short. So, what is binary search tree? So it is a binary tree. It is a binary tree where the key at any node V is at least as large as in this any key, or say all keys in left subtree and at most all keys in right subtree. Okay, so here is the node V, and it has a left subtree which is there various keys here in various nodes, and there is a right subtree which has various keys here in various nodes. So the key at V, the data at V, will be at least as large as all the keys present in the left subtree, and it's the key at V is at most all the keys that are present on the right subtree. So it is a binary tree where keys cannot be arbitrary. So keys has to satisfy this particular condition, and that is called a binary search tree. Now let's see why searching can be searching can be fast. Why we may not need to look at all the keys. So let's take an example. Maybe here is again 7. What could be the left one? Left one could be, say, it can't be more than 7, so it is 5. And what could be the right one of 5? It can't be less than 7, but it has to be more than 5. So maybe let's write 6. What could be the left of 3? It can't be more than 7, and it can't be more than 5. It has to be less than 5. So let's write it 3. Maybe 4 here, similarly 10, I don't know, 8. So this particular condition has to be satisfied for every node V. For any node V, for all the nodes V, this particular condition has to be satisfied. This has to be satisfied for this node 7, this has to be satisfied for this node 5, for this node 10, for this node 6, and so on and so forth. For all the nodes, this condition has to be satisfied. Now suppose this is a binary search tree. You can verify that it is a binary search tree. The condition of binary search tree is satisfied at every node. And now suppose I want to look for a key, say 1, which is not present, but let me tell you how to search for it. So what I do is that I look at the root node, and if I have already found it in the root node, then I return. Otherwise, I would compare 1 with 7. 1 is less than 7, so I know that if 1 is at all present, it has to be there in the left subtree. It cannot be there in the right subtree. So I don't have to look at so I don't have to look at the right subtree. Okay, so that's how I can prune the tree, how I can prune my search. And next, when I come to 5, again it is smaller than 5. I don't have to look at the right subtree of 6, right subtree of 5, and so on. Okay, so here maybe a pseudocode of find, where I am given a root node and a key. Okay, now if the data at root node is the key, then then return say root. Okay. So, if this is not the case, then I look at the appropriate subtree. If root dot data is more than key, that means key is smaller than the data at root node, then I don't need to look at the right subtree. So, I recursively find it. So, return find root dot left. In the left subtree I find the key, and if or else return find root dot right. Okay. So, that is the pseudocode of this find. Now, let us see why this find. We have seen that this find need not look at does not need to look at all the nodes in the tree, because the data is arranged in some particular order. But are we achieving log-n? As I said, that the initial motivation, one of the motivation for looking for another data structure is to perform the fundamental operations in log-n time. So, what is the worst case time complexity of find? So, I would let you think that the time complexity of find is order the depth of the tree. We will analyze why the relationship between depth and the number of data points n. Okay. So, that's how I perform find in a binary search tree. Then the other two fundamental operations is, one is insert. This we need to build the tree. So, and another is delete. So, let us first see what is insert. So, before writing the pseudocode, let me give you an example. So, maybe let us take the same example and let us try to insert an element in this particular binary search tree. Now, suppose let us try to insert. Let us delete this part also. Okay, it is not so intelligent. Now, suppose I want to insert a key. Say insert, I don't know what, maybe let us insert 9. So, let us add 9 here. So, what I would do the first step is to search for the 9. So, what is it? So, I start at 7, 9 is more than 7. So, I do not need to search in the left subtree, I go to the right subtree. I come to 10 and 9 is less than 10. So, I do not need to go to the right subtree of 10, I come to left and it is 8 and it is a leaf node. When I reach a leaf node and I have not found the key, then I insert it in an appropriate place. Okay, so for the time being, let's make a simplifying assumption that duplicate keys are not allowed. I let you think that all the things, all the operations and all the algorithms that we discuss in binary search tree can be easily handled, can be easily tweaked or easily modified appropriately to allow duplicate keys. So for us, insert is very simple. You first find the node. You look for the node, and if you have found it, then you don't insert it, because duplicates are not allowed. And if you have not found it, then your search must terminate at a particular leaf node, and there you insert the new element either as a left child if it is less than the value of the node where your search terminated, or otherwise you put it on as a right child. Okay, so let me not write the pseudocode. It is very simple. And and now, what is the again time complexity of this of insert? Time complexity, again, as you see, the worst case time complexity is the maximum depth of any node, maximum depth of any leaf node, which is same as the maximum depth of any node, which is the depth of the tree. So again, this is time complexity is order depth. Now let's come to delete, which is often the most non-trivial among the operations. So let's see what is the delete operation. So again, suppose I am given a tree. So let's see, suppose I am given this particular tree again. Okay. So easy things first. So maybe suppose I need to delete. Suppose I am asked to delete, say, 4. I am asked to delete some node which is a leaf node. So what I do is that again I always start from a root node, like linked list. In linked list I had pointer to, I only have a pointer to the starting first node of the linked list. Similarly, for a tree I only have a pointer to the root node of the tree, and from there I can traverse all the nodes in the tree. So I always start with the root node. When I store a tree, that means I maintain a pointer to the root node of the tree. Okay, and I look for 4. So 4 is less than 7. So I should come left. I should come left, and then it is I am here at 5, and 4 is again less than 5. So I come to left, which is 3, and and 4 is more than 3, so I come at 4, and it turns out that 4 is a leaf node. If it is a leaf node, what I do is that I simply delete it. Deleting any leaf node does not affect the binary search tree conditions of any node. So this is easy. Deleting leaf node is easy. So let's rewind. Now the next slightly non-trivial task is, so I am asked to delete a node which is, let me modify the tree slightly to make it more non-trivial, more non-trivial looking at least. Let's call it 3.5 here, and here I have 4.5. Suppose this is the tree, and I am asked to delete a node which has only one child. Suppose I am asked to delete 3. Then what I do is that again I look for the element 3 here in this tree. Search, I start my search at 7, come to 5, and I found 3. And 3 is not a leaf node. I can't simply delete it because it has children. So, but I observe that it has one children. Now, if it has one children, thing is very easy in some sense. Thing are still very easy. So what I do is that what I do is that I sort of delete 3, and 3 was the left child of 5. So, and 3 has only one children, and 3 has only one child. So that child I assign to its grandparent. So 5 lost is its left child 3. So I am assigning the child of 3, which is 4, as the left child of 5. Okay, so that is the thing. So if the key that you are deleting is an internal node and it has only one child, so if it does not have any child, then that means it's a leaf node, and that is very easy. You can simply delete it. If it has only one child, then also it is easy because you can simply delete it, and it has one child. That child get attached to its parent, to the parent of the node that you are deleting. Okay, so that's how. Then 4 is the left child of 5, and again it is very easy to check that all the binary search tree conditions, that at every node the key should be greater than all the keys in the left subtree and less than all the keys of the right subtree, that again continues to hold. Okay, so that is also fine. Deleting a node which has at most one child is easy. Then again, now the non-trivial part is, suppose I want to delete a node which has exactly 2 children. So suppose I want to delete 5. How should I delete 5? I would recommend you to pause this video and think, how can I delete 5? Okay, let me explain how I delete 5. Again, the first step is always search for the node. Go to the node. So I start at 7 and come to 5, and I see that it has 2 children. I can't simply delete it, and because it has 2 children, the previous trick for one children does not work. The previous trick for the nodes which has exactly one child does not work. So here is another trick. So the idea is that can we sort of swap the some nodes, so that this 5 becomes one of the easy case. So we have two easy cases. One is the node does not have any children, it is a leaf node. The second easy case is it has at most one children. Okay. Now how can I swap this and ensure that it has only one children? So here are two possibilities. One is, let me tell you one and you will think another one. So one is that you go to the left subtree and find the maximum of this subtree, which is 4.5 here. I would let you think how, or it is very easy how to find a maximum of an element in a binary search tree. So you look at the left subtree of 5 and find the maximum, and you exchange them. So exchange 5 and 4.5. Again, I would let you check that after this exchange also, the new tree is also a valid binary search tree. It satisfies all the conditions. Okay, and now what we have achieved is that, again you check that the max node can have at most one child. In this case it is a leaf node, but it can have at most one child, which has to be left child. Which we don't need this extra fact here, but you can check that which has to be left child. It can't have a right child. Why? Very easy. Again, I would recommend you to pause and think before listening to my answer. Okay, so it can't have a right child because if there exists a right child here, then the key is not maximum of that subtree. That would contradict our assumption that that is a max node. Okay, so let's summarize how you delete an element which has exactly two children. You swap that with the maximum element of left subtree, and then because of this observation that the max node in the left subtree cannot have any right child, so in particular it can have at most one child. So so we are back to a easy case, back to the easy case where the node that we are deleting has at most one child. Okay, so what is the time complexity? The first step is find. The second step is that you go to the left part and go to the left subtree and find the max. I would let you check that this max can be found in order depth time, and then you swap, and then again you delete. So all these operations can be performed in order depth time. So time complexity order depth. Okay. Now what is that? Now once now we have discussed all the operations for binary search tree. There are some more fancy operations like given two nodes, can you find whether whether one node is successor of another one or not? Called given a binary search tree, can you find the minimum or can you find the maximum, and so on and so forth. There are various other kinds of operations, and those again those are cute exercises, but these three are the fundamental data structure data structure operations. These operations you need to use this binary search tree data structure. Now what is the depth? Now let's focus only on binary search tree, and let's see two extreme cases. So depth is the length of a maximum path. Now in the worst case or the tree could simply look like a path, maybe 1, 2, 4, 5 and so on. This is a valid binary search tree, but here n, the number of nodes, is depth minus 1. Okay, so depth could be as large as so what we have seen that depth. So from this example we conclude that depth is less than equal to n minus 1, n plus 1, because by definition of depth there exists a path which involves n edges, and if it has to involve n edges there must be n plus 1, there must be at least n plus 1, there must be at least n plus 1 nodes in the tree. So depth is less than equal to n plus 1. The number of nodes could be more. We can have some more children of various nodes. So that is a upper bound for depth, which is tight because of this example. In general, this upper bound cannot be improved. This is the tight example. What is the lower bound? How small the depth can be? So depth is like, I have a Depth basically says that you have a path which has depth plus 1 nodes, and there is no path of longer length. Okay, so this is sort of the level. Now how many nodes you can pack here? You can try to maximize the usage, and all make all the children, all the non-leaf node has 2 children. So this is depth plus 1. Okay, and let's see what is the number of nodes here. Here this is 1, the first level. In the second level it is 2, the third level it will be 2 square, and so in the last level, in the depth plus 1 level, it will be 2 to the power, let's call it d for depth, 2 to the power d. Okay, and so what is the number of nodes? Is, if you sum it up, this is summation 2 to the power I equal to 0 to d, which is 2 to the power d plus 1 minus 1. Okay, so these could be the number of nodes. So the number of nodes can't be more than this. So what we have is 2 to the power d plus 1 minus 1. This is the maximum number of nodes. So this is greater than equal to n, where n is the number of nodes. So what we have here is d is greater than equal to 1 plus log of n plus 1 base 2. Okay, so as we see that if the tree is balanced, that if the tree is not so skewed like this, then our operations are fast. Then our operations, if somehow we can ensure that the tree is reasonably balanced, or at least good balanced, or say for simplicity, let's assume that if we can ensure that the tree is completely balanced, that means what? That means all leaf nodes are at the same depth. At least in this case, we see that all the operations will take order log n time. But the worst case complexity still becomes n, because depth could be as large as n, as this tight example shows. Okay, so next in later lectures we will see some more sophisticated binary search trees, which are called, say, AVL trees. There exist sophisticated binary search trees, which is AVL trees and red black trees, and there are plenty more. We will see one example, one of them. And those trees, what they ensure is that after every insert and delete, they will sort of ensure that the tree is sort of reasonably balanced, in the sense that if there are n nodes, the height is roughly order log n, or depth is roughly order log n. And now if the depth is roughly order log n, then all insert delete all takes order log n time, provided that the extra work that you are doing for ensuring that the depth remains order log n, depth of the tree remains order log n, can be done in order log n time, or reasonably fast, which they do. And this binary search trees clubbed with those sophisticated binary search trees ensures that all these basic operations like insert, delete and find can be performed in order log n time. Okay, thank you.